On Monday, you took a look at the 10% condition. And the purpose of the 10% condition is when I am sampling or performing repeated trials, I can treat those things as independent as long as my sample is less than 10% of the population. So for example, if you are doing a sample of students at Rancho San Juan and you sampled 30 students is much less than 10% of 1,500. Because 10% would be 150. 30 is much less than that. So you would be fine in treating those 30 people as independent selections from the population. Yeah? That does not, as a statistician, mean we want a smaller sample size. Right? Bigger sample sizes are always better because they're more representative. It just means that if they're not less than 10% of the population, I can't treat them as independent. I have to treat them differently. I cannot use the independent methods we're talking about. Okay, so today we're going to focus on our last discrete probability distribution, the geometric distribution. And the geometric distribution follows most of BINS. So let's review BINS from last week. What does the B stand for? Binary. Same thing is true here, and I forgot to stick it in the notes. We want this to be binary. Two possible outcomes. What do we call those possible outcomes? Success and failure. Perfect. No judgment there, right? Just success is what we're looking for. Failure is what we're not looking for. Good. So we took care of the B in BINS. What does the I stand for? Independent trials. Very good. Same thing for geometric distributions. We want our trials to be independent. What does the N stand for? Number of trials. That was the thing we were keeping track of with a binomial distribution. How many trials were successes out of N trials? Now we are counting the number of trials until a success occurs. So binomial has a fixed number of trials, and I keep track of the number of successful trials. Here, I keep track of the number of trials until a success appears. How many times do I have to flip the coin until I see a heads? How many times do I have to roll the dice until I see doubles? Yeah. And then the S, what does the S in BINS stand for? Same, yeah, same probability for each trial. If I could spell. Probability of success is the same for every trial. Flipping heads, right, is 50% every time. The coin doesn't care whether it was the first flip or the 10th flip. Good. So, the random variable X, if it is geometric, it is keeping account of the number of trials it takes to get a success. That is how we tell binary from geometric, because everything else is the same. Are we keeping track of the number of successes or the number of trials it takes to get a success? Number of successes is binomial. Number of trials till success is geometric. The probability distribution of X is a geometric distribution. And the possible values of X start with what? What is the minimum number of trials I need to flip a heads? 1. Geometric distributions start with 1. Binomials start with 0. Because if I'm keeping track of the number of heads I flip, it's possible I don't flip any, which would be 0. But if I'm keeping track of the number of trials I need to flip heads, I have to flip it at least once, otherwise I get nothing. And then another question. So we know we can have 1, 2, 3, 4. What's the upper limit? With binomial, it was n, the number of trials. Where do I stop here? Yeah, but how do I know where that happens? Yeah, infinity is correct. This thing just keeps going and going and going. It is possible, if I am very unlucky, that I don't get a heads until the millionth flip of that penny. It's not likely, but it's possible. So this keeps going and going and going. At some point, the probability is so small it rounds to 0, at which points we stop caring. But we have to go up pretty far to find that. Yeah. Good. So we're going to do an example. You might want one person from every table to grab a textbook because we're looking at example from the book. It is on page 431. 431. I'm assuming I saved it for myself. Oh, I did. Look at me. All right, while we're getting situated, you are looking for page 431. We are looking at the Is This Your Lucky Day? We are considering a hypothetical classroom, Mr. Santoyo's class. Mr. Santoyo is planning on giving 10 problems for homework. As an alternative, students can select to play the Lucky Day game. Here's how it works. A student will be selected at random from your class and asked to pick a day of the week. Your teacher will then use technology to randomly choose a day of the week as the lucky day. If the student picks the correct day, the class only has one homework problem. Yay! If the student picks the wrong day, we repeat the process. Calculator chooses a random number. Random student chooses a number. We check if those days of the week match. If they do match, then we only have 2 homework problems because that's the second trial that we won on, and so on. So the number of homework problems that the students in Mr. Santoyo's class will have corresponds with the trial where we get our first match. Yeah? So I'm going to use my calculator to select a number between 1 and 7 using randint. Yeah, so I mean, it can choose repeat. We might get the same lucky day. And then I'm going to use a name spinner to choose a random student to pick a day out of the week that they feel is appropriate. Yeah? So I'm using randint 1 through 7. I'm going to choose 1 at a time. We're going to see how this goes. So I have my lucky day. Who's going to guess first? Oh, that's 5th period. That's not helpful. You guys aren't 5th period. Sixth period. There we go. More names. Bigger class. Samuel, what day do you pick? Saturday is not correct. My calculator picked Monday. I'm sorry. So I am picking a new day. Yes? It may be Monday, like it was this time. It may not be. And a new student to make a guess on a day. Sophia, what day do you pick? Wednesday is incorrect. My calculator chose Friday. Oh. Okay. I have picked a fresh choice from the numbers 1 through 7, Monday through Sunday. I don't know. Ricardo. Which day? Sunday is not correct. My calculator chose Friday. All right, I've chosen a fresh lucky day. Let's see who's going to guess. Jaylene, what do you guess? Is not correct. My calculator chose Monday. I'm sorry. I know. I'm sorry. Senia, give us a day of the week. Is not correct. My calculator chose Tuesday. All right. I marked that. Yes, I did. Next one. Valeria, pick a day of the week. Close. My calculator chose Thursday. So close. Choosing without replacement, or with replacement rather. Sophia? So close. It chose Wednesday this time. Because that changes the probability between each guess. They won't be independent. Samuel, choose a day. Tuesday is correct. Yay! Good job, Samuel. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. We guessed correct on the 8th trial. That means Mr. Santoyo's class would have 8 homework problems. Yay! So I want you to take about 90 seconds in your small group and describe what we just did. What happened? What did we see? We know what the result was, right? Guessed correctly on the 8th trial. But what else was happening? It's 60 more seconds. Okay. So we're going to check bins really quick. What are the 2 possible outcomes on a guess? Success and failure. You guess correctly, you guess incorrectly. Were the trials independent? Yes. It was a new random number from a fresh deck of 7 days each time. Was the probability of success the same for each trial? Yes, because we were choosing from a fresh set of 7 numbers. So I know my probability of success was 1 out of 7. Out of curiosity, if my probability of guessing correctly was 1 out of 7, come on, pen. I don't have the patience for this today. What is our probability of failure? 6. I know. This is the 3rd period I've had to do that today, too. And then the question for the N, because we skipped the N in bins, is what were we keeping track of? What was our random variable here? Number of trials until we guessed correctly. Good. Meaning this checks all the boxes of a geometric distribution. So X is geometric. And geometric doesn't have a number of trials. It only cares about probability of success. And we're going to talk about how to calculate probability. So we're going to do some thought experiments based on our lucky day game. Based on what we know about our system, what is the probability we select the lucky day on the first try? 1/7. 1 trial, 1 out of 7 chance I guess correctly. Yes, I agree. Very good. If we had guessed correctly on the first trial, we would have stopped. So this is a fresh consideration here. What is the probability that I didn't guess correctly until the second trial? And this is 2 fractions. Incorrect first and correct second. What's the probability that I was incorrect on the first? 6 out of 7. Correct on the second. 1 out of 7. We repeat, third trial. Probability I guessed correctly on the third trial. Yep. 6, 7 times 6, 7 times 1, 7. Yeah. Good. There is a pattern here. There is a pattern here. I'm going to give you about 90 seconds in your small group to see if you can suss out the pattern, and then we will write it together. I don't know, I have to come closer and hear the whole thought process.
Probability of x minus 1 times probability of not success times probability of success.
On the right track. But remember that shorthand for repeated multiplication of the same number is not x minus 1 times p. If I had x times x times x, how would I write that? 3x? X to the power of, yeah. Good. Some of us have spotted the pattern. When we do geometric, we have a whole long string of failures. And then we finally get a success. If I do X trials, my success occurred on the 10th trial. How many failures happened? 9. If I did 100 trials before I saw my first success, how many failures? 99. So this is q to the x minus 1. That's the number of trials that I got a failure, times the last trial, which is a success. This is just a big long string of multiplication rules. First trial is a loss, and second trial is a loss, and third trial is a loss, and last trial is a success. Big long string of multiplying. Yeah? Much less scary than binomial, which had factorials and combinatorics in it. So this one is less scary conceptually. We're going to do another example because it's good for us. Yay. So after a quick discussion, Mr. Santoyo's class decided not to play the Lucky Day game because they didn't want to risk getting more than 10 homework problems. Did the class make a good decision? And as statisticians, we need to answer that with numbers. So we're going to calculate some probabilities. First one says, find the probability that the class receives exactly 10 homework problems. Meaning we guessed correctly on the 10th trial. Raise your hand if you can tell me what that looks like. I'm going to give Drew a chance because you got the formula correct. Yes, Drew.
6 out of 7 to the power of 10 minus 1 times 7.
Can I get a thumbs up if we agree? Yeah, very good. 10 trials means 9 failures. 6 out of 7 to the 9th times that 1 success on the 10th. Perfect. We're going to slap that in our calculator and get an answer. And I get 0.036. Somebody should check my math. Good. So the probability that I got the first guess on the 10th trial is only like 3.6%. But really that doesn't answer our question. Our question is, what is the probability that Mr. Santoyo's class had less than the 10 problems he originally planned to assign? So B is saying find px is less than 10. I'm going to rewrite that in terms of a less than or equal to. If I want all of the numbers less than 10, what is the biggest number included? 9. So this is less than or equal to 9. So I'm going to use the formula. This is I won on the first trial, or I guessed correctly on the second trial, or I guessed correctly on the third trial, or all the way up to the 9th trial. So the what? Yes, you may. Did you make any hot pass? Girl. While I'm filling out this EHAW pass, do we agree with what I wrote up there? Yes, matches the pattern. I need to account for all of the outcomes between 1 and 9. I don't want to calculate that by hand. That's a lot of typing because I got to do all the values between 1 and 9. I'm lazy, so we're going to use our TI-84 calculator to find that for us. And the question is, how do I get to the distribution menu on my calculator? Second and vars. Very good. Second vars. Because above the vars button in blue, it says DISTR, distribution. And if you go all the way down to the bottom, the last two options are Geomet PDF and Geomet CDF. PDF finds a single trial. CDF finds a cumulative across a range of trials, less than or equal to. What two values are those functions asking for? P and X value. Good. I need to know the probability of success. I need to know which trial I want that success to occur in. For us, PDF or CDF? CDF. So this is Geomet CDF. My probability of success is 1/7. My X value, which is the upper range, is 9. I'm going to give you a second to do that on your calculator. I know it's going to be 0 point something. $0.750. Yay! Which means for Mr. Santoyo's class, there is a 75% chance that they will have 9 or fewer homework questions. 75% chance that their homework assignment is shorter than it would have been originally. Did his class make a good decision in choosing not to play? No, odds are better than half that you're going to end up with less homework than you would have originally been assigned. Yeah. Good. Good. All right, so let's talk about how we describe these distributions. We know when we're describing distributions, we use 3 of the 4 letters from SOX. We skip the O. We don't look at outliers. But what do we look at? Shape, center, spread. Very good. Shape, center, spread. And we know for probability distributions, mean for center, standard deviation for spread. Those are the defaults. For shape, what type of graph do I want to look at? Loud and with confidence. Histograms. That was not very confident. Histogram is the gold standard for quantitative data. Yeah, histogram. Just like the binomial, geometric gets shortcut formulas for its mean and standard deviation. For the mean, it is the reciprocal of the probability of success, 1 over p. For our lucky day game, the probability of success was 1/7, 1 over 7. What is the reciprocal of 1 over 7? 7. So we expect over a long number of lucky day games, there's an average first success, first correct guess, on the 7th try. We were just above that with 8. My third period got it on the 7th. My second period gave up after 10. They were not very lucky this morning. Yeah, they were definitely in the 25. They agreed that Mr. Santoya's class should not have that. For standard deviation, we also get a shortcut formula. It is the square root of Q divided by P. You will notice that P is not under the square root. So when you are plugging this in a calculator, parentheses around the numerator, parentheses around the denominator, because your calculator is dumb. Please stop playing with your cell phone. You already look gorgeous. You don't need your cell phone to check your makeup in 6th period. So let's do an example. We saw this, I believe, the end of last week. Local fast food restaurant is running the draw a 3 get it free lunch promotion. Customer orders, touchscreen displays a message, press here to win a free lunch. Computer program simulates 1 card being drawn. Card is a 3, you get a free lunch. Card is not free, you have to pay your bill. Yay. We are keeping track of the number of customers it takes to get the first free order on a given day. So we go down the checklist. Is this binary? Yes, what are my outcomes? Free lunch or not free lunch? Good. Free lunch or pay bill? Are the trials independent? Yes, separate customers, separate bills, separate run of the program. Probability of success the same for each trial. Yes, 4 3s out of a deck of 52 cards for each draw. And then N, we look at what we're keeping track of. So what is our random variable keeping track of? Number of customers until first free lunch. Yeah. We are keeping track of a number of trials I need until I see a success, a free lunch. So that tells me that this is geometric instead of binary, because it meets the B, the I, and the S, but that N is not a fixed number of trials, it's a number of trials until I see a success. Good, so this is asking us to do 3 things. We want to construct a histogram for x is 1 to x is 10, describe the shape, and then find the mean and standard deviation, interpret those values. We will start with the histogram. So before I do that, I'm going to write the distribution. X follows a geometric distribution. Geometric distributions only need a probability of success. I'm drawing 3s from a deck of cards. So there are 4 3s out of 52 cards in the deck, 4 ways to win. I am asked to make a histogram. Before that, I need a probability distribution. I'm starting at 1. They told me to go all the way up to 10. So my suggestion, so that you don't have to do the formula 10 times, is you go to your calculator, you go to the list menu, right? Stat button, enter. You put X values in list 1. And then you are going to go up to the header for list 2, and you are going to enter Geomet PDF. Because I want to calculate the probability for one number at a time. I know my success, my P is 4 out of 52. I know that my X values are coming from list 1. If you do that, it should auto-populate list 2 with the probabilities for X is 1 through X is 10. I'm going to give you a second to do that, and then I'm going to start filling in the table. I am going to round values to 2 decimal places, because I am lazy and we're doing this quick. Calculators? It's a whole table without calculators? Oh, my soul is crushed. One calculator? No calculators? Oh. No calculator. It's like a third of the class doesn't have their calculators today. Frowny face. So rounded to 2 decimal places, that's what I got. Can I get a thumbs up if anybody else got that? I see a couple of thumbs up popping up around the room. Very good, thank you. Normally, we wouldn't round to 2 decimal places. We know probabilities usually rounded to 3 or 4, but the point of this question wasn't, can I draw a histogram? It's, can I describe the shape? So rounding is fine, just to get a general idea of what the shape is. Remember, on the FRQs, you have to make a balance between precision and time. So if the point of the question is not the histogram, but something else, and this is just a tool, you can make it a little rough and messy. Now I'm going to draw it, 2 axes. What goes on the x-axis? Random variable, very good. I need to go between 1 and 10. Number of customers until we get a free lunch. What goes on the y-axis? Probability, very good. This is a p of x-axis. And my biggest probability is 0.08. So 0.00, 0.08. So half is 0.04. Half and half is 0.02 and 6, half, 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 half. You like even numbers. Dividing things in half is easy. When we draw our bars, the bars have the label centered in the middle, and the height of the bar corresponds with the probability for that bin. So starting with our first bin, the probability that I get my first free lunch on that first customer is 0.08. So all the way up to the top. Probability of getting it on the second or the third is 0.07. So my next two bins stop at 0.07, which is there. The next two bins after that are 0.06. Next two bins after that are 0.05. And then the last three bins are all the same height at 0.04. Why are you abusing your calculator, Jennifer? What did it do to you today? You're bored. Oh, sad face. Here, abuse the watermelon. All right, we were asked, what shape does that graph make? Right skew. Right skew. Is my pen black? Yes, it is. Remember that the direction of skewness follows the tail and not the peak. Peak is on the far left. Long tail goes to the right. This is right skewed. So my mean is going to be to the right of the median. My mean is out that way. Next, they ask us, let's find the mean. Where is the mean? How do we interpret it? Reciprocal of the probability. Very good. 1 over p, 1 over 4 over 52, which is 52 over 4. I happen to be familiar with the structure of a deck of cards, and I know that that is 13. Magic just happened. That's what happened. The mean is the reciprocal of the probability of success. Take the probability of success fraction and flip it upside down. Probability of success was 4 out of 52. Mean is 52 out of 4, which is 13 on your calculator. If I were to interpret that, that means if I were to look at many days of this pick 3 get free promotion, I would expect that the average first free lunch happened for the 13th customer. Won't be the 13th customer every day, but that will be the mean of all of the days. No, I'm not writing that down because I'm tired. B, similar idea, find and interpret the standard deviation. Who remembers how to find standard deviation? Square root of q over p. So square root of 4 out of, no, not 4. 48 out of 52 over 4 out of 52. Again, a reminder, parentheses are your friends. I should have just calculated it, but I decided to go back, and now I'm stuck. Where is it? I'm getting thumbs up. 12.49, about 12 and a half. Which tells me my spread's pretty big because the average is sitting at 13, but that middle chunk of my data is between half a person and 26 and a half people, right? So that's a very big spread. And we can kind of see that in the graph because it is slowly dropping. It's not like a sharp decrease. It's just a little bit of a trickle. So I expect that even though I stopped at 10, this is a slow trickle down towards the x-axis, and it's going to go out for a while, all the way out into the 20s before we start dipping really low. Oh my gosh, you guys are so much faster than my other classes. We're going to do this last question as a warm-up on Monday. So you can ignore this last example. And that's going to give you a couple minutes of homework time. Can you what? You want to play the Lucky Day game again? Okay. I need somebody who's going to be the record keeper for who's guessing correct. Who wants to keep track? Okay, thank you, Addie. Oh, lucky you. All right. For Lucky Day game reminders, I'm going to pick a day from 1 to 7. 1's a Monday, 7's a Sunday. I'm going to call a random name. You're going to guess a day. Addie's going to keep track whether they guess correctly or not. Yes? All right. I have picked my first lucky day. Let's see who's going to guess. How many times can Samuel guess? Samuel, what do you guess? Wednesday is not correct. My calculator had selected Tuesday. Amy, pick a day. Amy picked Saturday. Amy is also incorrect. My calculator picked Monday.
Oh my gosh.
Valeria, give me a day. Saturday is not correct. My calculator chose Thursday. Ivan, give us a day. Incorrect. My calculator chose Saturday. You get a redemption arc here. What are you giving us? So close. Wednesday was the lucky day. Eileen, give us a day. Sunday is not correct. I know. Yari, pick a day. Lucky day is not Tuesday. New lucky day, new guess. Bree, pick a day. So close. My calculator chose Wednesday. Katie. Nope.
My birthday was Sunday.
Not Sunday. It was Tuesday that time. Chris, give us a day. Not even close. Katie, you get to go again.
I'm gonna go on
Oh, Ivan. That's not a Wednesday. Eileen. So close. It was a Thursday. Oh. Okay. Let's go change our settings and we'll start removing people.
Oh my god.
Nope. Not a Saturday. Nope. Not Saturday. We're not having as good a luck this time around. Jacob's not here. That doesn't count.
Katie. Okay. No, I'm gonna say Sunday.
Cammy, give me a day. Day of the week. Not Wednesday. Do we run out of people before we run out of lucky days? Nope. Now you know how my second period felt. Jada, give me a day of the week. Not Monday. All right, Ricardo. Which day? Not Thursday. Austin, it is Tuesday! Yay! Addie, how many trials did that take? More than 10, that's for sure. Getting a long homework assignment. 23, that's more than double the original assignment. Oh.